Okay, welcome all to this tutorial on large language models. Sorry for the bit of the delay in starting because we're trying to solve technical problems, which evidently always there is. But now that we have gotten over the technical glitches, so I guess we could start. And we are going to have like short presentations, starting with the history of NLP and gradually moving towards the more advanced techniques in NLP that we all work on nowadays. So this tutorial is going to be covered by 5 speakers. So they will in turn talk about their topics, starting right from the history of NLP and then moving on towards other more advanced topics. So I think the first speaker is Sudeep Nuster. So Sudeep, can you hear us?
Yes, I can. Can you hear me?
Yes. So I guess you have a copy of the slides. So, or do you want us to share the slides and then?
I can share my screen from here. That will be more convenient for me.
Okay, right.
Is it?
Yes. Going to the full screen. Yes. So yeah, you can start your part whenever you're ready.
Okay. A very good morning to you all, and I will take about 10 minutes to tell about or give a very brief introduction into natural language processing. So what is natural language processing? Natural language processing is essentially nothing but processing of natural language text or natural language contents. Then what makes NLP difficult, or rather, why should we bother about natural language processing? Because, we humans are very intelligent, and even an illiterate person without the knowledge of ABCD can make perfect sense of language in his or her mother tongue. But a machine is a dumb thing. So how can you make a machine make sense of natural language content? That's basically the question. So in one word, the answer to this is ambiguity, because natural language processing, natural language is extremely ambiguous. So this makes the task difficult. If there was no ambiguity in natural language, then it would have been very easy to build NLP systems or applications. So this is the classical model of NLP, where at the bottom you deal with morphology. So this is called the morphological analysis or lexical analysis. Then you deal with the syntax, which is called syntactic analysis. Then comes the semantics, or which is referred to as semantics analysis. Typically, most of the NLP applications has these 3 layers of processing, but some applications require much deeper investigation into the contents, the textual contents, so which requires dealing with pragmatics and discourse. And those of you who have studied compiler, you know that in compiler also you deal with lexical analysis, syntactic analysis, and semantic analysis. It's the same. You are dealing with language, you will have to deal with these 3 layers of processing. Now, I will present some ambiguities in each of these just to motivate the case, like why you should bother about NLP, why it is challenging, why it is difficult. So I will give some cases of ambiguity in each layer of processing in lexical analysis, syntactic analysis, and semantic analysis. So say, for example, the word dryer. Okay, so you know that dryer could refer to the adjective more dry or the machine which dries. So if it refers to the machine dryer, then the lemma is dryer itself, not dry. Okay, so you will basically have to decide on the lemma. So whether it is dry or dryer itself. Then words can represent or they can belong to multiple part of speech. Say, for example, the word sheep can be a noun or a verb. The word round in English is a very, very ambiguous word. It can be a noun, verb, adjective, preposition, and I think a adverb. Okay. So similarly, words can have multiple meanings. When you are dealing with polysemous words, they can have multiple meanings, and you'll have to identify the exact sense in the context. Okay, and how do we disambiguate? We look at the context. The context is all you have to disambiguate all the ambiguities that are present in the text. Okay, say for example, John kicked a ball. You know that kick is a transitive verb and it requires a physical thing. So you know that In this case, ball refers to some football or some other ball, okay, physical ball. But the ball lasted until midnight. In this case, lasted requires an event as the subject. So you know that this must be referring to ball dance. But if you look at the last example, when you hold a ball, in this case, you don't even have enough context to disambiguate the meaning of the ball, because even the word hold can be ambiguous. You can either hold a ball physically, or you can arrange a ball dance. Okay, so you can have both interpretations. So you need further context to disambiguate in this particular case. Structural ambiguity appears when you can associate multiple syntactic structure with a sentence. Okay, so for example, take the first example. I do not have enough time to go through all these examples, but we will share this slide so you can go through the examples yourselves and try to identify the ambiguities. Say in the first example, the act of flying planes can be dangerous. So the verb flying is the subject, or it could mean that planes that are flying can be dangerous as opposed to planes that are grounded. Okay. Similarly, the rest of the examples. The last example is a classical example in NLP, where you have this what you call PP attachment, or prepositional phrase attachment. So when you are generating the parse tree for a text, so say for example, with a telescope is a prepositional phrase, you will have a small subtree for this. Where do you attach this subtree? So do you attach this subtree with the boy or the girl? Or so the question is, who had the telescope? The boy could have the telescope, the girl could have the telescope, or maybe it does not matter. Maybe the telescope was in the park. Okay, maybe the act of seeing was done with the telescope. In that case, you will associate the subtree with the verb saw. Okay, so these are the ambiguities that you will have to encounter in when doing parsing or syntactic analysis. Semantic ambiguity basically appears from the fact that words are polysemous. In fact, most of the frequent words that you use on a daily basis are very, very polysemous. They have multiple interpretations. In this example, both bank and interest, they are used in totally different senses. So how do you know, or how do you disambiguate the appropriate sense for these polysemous words? That's basically the semantic ambiguity. Similarly, you will also have to deal with multi-word units. So like phrasal verbs, idioms. Particularly idioms are very challenging in natural languages, because the meaning of the idioms cannot be made up from its constituent words. Co-reference resolution, that in natural language, we very frequently use pronouns. So pronouns are very frequent, just like function words. But pronouns do not have any existence of their own. So here the problem is, you will have to identify who a particular pronoun is referring to. So if you look at the first all these examples. So them, in the first case, them refers to the, I think, some of the people in the crowd. And in the second one, them is referring to some of the fire, maybe, or maybe it could even refer to the police. And particularly when you're building a chatbots or some other applications that require pragmatics or discourse analysis, in those cases, typically we do natural language processing with at sentence level. But when you are going beyond sentence level, deal with this co-reference resolution. Here are some more examples of ambiguity. If you look into this, you might discuss the last one, NLP. What do you think about about NLP? All of you, each of you know what NLP is. But do you see any ambiguity in this? Even the very term natural language processing is ambiguous. So the interpretation that we take is processing of natural language, right? But the other interpretation could be language processing, which is natural. Okay, so but we humans are so intelligent that we do not even see this ambiguity in this. We always think of the correct interpretation. We always take the correct interpretation. Take the example, a sentence. Machines' artificial language processing abilities cannot match humans' natural language processing abilities. In this particular sentence, I mentioned natural language processing, but here the construction was language processing, which is natural, okay, which is as opposed to what we are talking about. We are talking about processing of natural language, okay. Language processing is, ambiguity. When you are doing language processing, you'll have to encounter ambiguities at every stage. It is pervasive. Say, for example, in this particular utterance, I made her duck. It has multiple interpretations, at least 5 interpretations that I have listed here. Then speech processing is also considered language processing, is because speech is nothing but another modality of language. So you have text and then you can also have speech, another modality. But when you are dealing with speech processing, it is much more difficult because you are dealing with continuous signals. So in when you are doing natural language processing with text, you are only dealing with the alphabets. Okay, so which is a very small finite set of characters. Take the example, same example, I made a duck. If you build an ACE or automatic speech recognizer, so you can have all these sentences on the left, which sound very similar to the original sentence. Okay, so how do you know that I mean, the ACE or output should be I made her duck, the one on the right? If you look at particularly the one highlighted with green, these two sentences also make the exact same pronunciation with the original sentence. No distinction whatsoever. So how do you know that these two sentences does not make any sense, and the one on the right is the perfect I mean, is the correct interpretation? So language models can help with that. We have some more examples. These are very complicated examples. If you go through them, because of the time constraint, I'm not going through all of them, but you will see the ambiguities. Why else is NLP difficult? Because you'll have to deal with non-standard English, like the ones that you find in social media contents. Then you might think that segmentation is a trivial case of processing, but it is not, because you'll have to deal with cases where you do not have space as the delimiter. Even with English, sometimes you will have to, I mean, if you look at the second example, here, New York and New Haven, they are separate tokens and they are co-joined by the hyphen. Okay. So this is the correct interpretation. Then you will have to deal with neologism, like the new words that are coming up these days. I mean, whenever you heard for the first time the word untrained, you perhaps knew what does it mean. But how does a computer know when does it when it deals with a new word? How does it make up the meaning for that word? And sometimes you'll also have to deal with. I mean. NLP, you might think that you only need linguistic knowledge to solve this problem, but sometimes you might need world knowledge, what you call world knowledge, to solve this problem. This is particularly relevant with natural language understanding, which is basically deeper natural language processing. And then entity names, identifying entity names is a very important task in natural language processing. And in English, it is rather easy, but if you go into other languages like Indian languages, you do not have the capitalization key. How do you identify, by example, I mean, the proper names? I give this example. I mean, I have a colleague named Komal Shorkar. How do you know that I mean, Komal and both and Komal and Shorkar are valid Bengali words. How do you know that? Say, for example, you are building a machine translation system. You should not, in this case, translate Kamal Sarkar to Lotus government. It should translate it as, you should rather transliterate it to Kamal Sarkar in English. Okay. These are some applications of NLP, like one information retrieval typically deals with what you understand by web search. And then information extraction covers a lot of things. It is a broad umbrella under which a lot of things comes, like text classification, summarization, relation extraction, knowledge extraction, and many other tasks. Some other examples of NLP, I mean, the applications of NLP: machine translation, question answering. You can have question answering on unstructured text, unstructured data like text, or you can have a question answering system on structured data. Like say, for example, you want to build a question answering system on a database or a knowledge base. Okay. Then text normalization. I mean, text normalization is typically considered a basic pre-processing task, but sometimes you can also build complete solutions or systems based on this, like the Spellchecker. I forgot the name of the Spellchecker. They are $1 billion company now. I think Grammarly. Yes, Grammarly. But I mean, the basic task of text normalization is basically you will have to bring the text to some standardized or normalized form. Okay. Similarly, grammar correction is also considered a task of text normalization. Again, if you are dealing with speech, in speech we have a lot of dispenses, and you will have to deal with. You will have to basically remove those dispenses from speech. Devashish, can you let me know how much time do I have? I will go accordingly. Okay, we'll go on. So some other examples of NLP, we have text similarity. Text similarity is a very broad term. You can either find text similarity between two words, a word pair or a sentence pair, or you can find text similarity between a pair of text. Okay, so some example solutions are like if you want to build a software for plagiarism detection, then you are essentially comparing the piece of text with a large corpus. Okay, so you are basically finding the similarity between a text pair, and it also has application in answer or essay grading, say you have a model answer, the paper setter has prepared a model answer, and you have the student answer. So basically, here the task is to build a system which can evaluate like a human expert or human evaluator. So it's essentially the task of text similarity. Okay, then readability assessment, finding the difficulty of a text. So whether a particular text is suitable for UG level or PG level or high school level or primary school level. And if the text is difficult, then how you can simplify the text to lower level students. Okay. Similarly, event extraction is another task in natural language processing. Say, for example, you have a news corpus and you want to build a knowledge base of events and like how the events went on. And then you also find out the causality relations between events, like which event led to which events and so on. Okay. The natural language generation is the task where you are generating natural language contents. Classical example of natural language generation is like say, for example, you want to build a system which takes image as input and it gives a description of the image. So that's a classic. I mean, classically it is defined as natural language generation takes as input some non-textual data and it generates output in some textual format. Okay. Similarly, depending on the domain you are dealing with, you can have different task. Like, say, for example, you are dealing with only financial text or legal text, then because those domains also throw some additional challenges to the task. Okay. And then you can also have multimodal processing, say, for example, where you deal with both text input and speech input together at the same time. And then we do some task. Say, for example, you are building a speech recognizer. Now we know that the speech is always not very, there must be some noise in the speech. And if you, in addition, you additionally have the video of the speaker, then you can do additionally the lip reading. So that helps. Even if in sometimes what happens is you don't have the speech at all, just by reading lips, you can interpret what the speaker is saying. Okay. So that's basically what is multimodal is. You are dealing with data from multiple modalities. Text classification, depending on the actual objective and the set of predefined classes, but you can have many different types of text classification. And then, in fact, most of the tasks that you will deal with in natural language processing are considered text classification tasks. In speech processing, the core two tasks are speech recognition, of where given a speech signal, you will have to transcribe the speech. And in speech synthesis, the speech signal, okay, maybe in male voice, maybe in female voice, or whatever. Okay, some additional it is typically considered a pattern recognition task. Then speech derivation is a speech joint task. Then you'll have to also deal with 100 rupees. Okay, so if you transcribe it, there will be two separate words, 1 and 100. But typically, if you write it down, it will be just 100. Okay, so that's the task of normalization in ASL. And if you're dealing with dialogue systems, you'll have to deal with all these tasks in speech. Devashish, how much time do I have? Devashish?
Can you hear me?
I did not. How much time do I have? I will go accordingly.
I think we already have taken 15 minutes, if I'm not mistaken.
Okay. I think then because the tutorial is quite short, so I will hand over it to Partho, who is the next presenter. Okay.
So till now, do you have any questions from the room for what Shudeep Noshkar covered on the basic introduction of NLP? If you have any questions, then we can take the questions, and then we can move on to more advanced sequence. So, yes, raise the question. Yes. How do we what? Phrases. So I guess the question is like how difficult is to handle phrases in NLP pipelines?
Well, it is not the typical. I mean, we in NLP we have something called shallow parser, which is like a less difficult task than I mean full parsing. So, say in shallow parser, or we typically call it also chunker. Okay, so it breaks the original text into phrases or chunks, but then you can have recursive phrases or recursive chunks, so one phrase within another phrase. But typically, dealing with phrases is not a difficult task. There are many other tasks, like parsing itself is a much more difficult task than identifying the phrases or dealing with the phrases.
Okay, so thanks a lot for the presentation.
Okay. Yeah.
I don't think there are any more questions in the room, so we can move on to the next speaker. So Marco, you have a copy of the slides?
Good morning, everyone.
Yeah, so if you can try sharing your screen and then.
Yeah, so should I just share from here? Okay, all right, just a moment. Can you see my screen?
Yes.
This is not going full screen somehow. I don't know, maybe this should work, right?
You can see your
Okay.
screen, yes.
This is my first slide. Let me start from here.
Yeah, okay.
So essentially, what we do in NLP is we try to represent the words in terms of some numbers. So several old techniques I'm going to show you initially, which are known as sparse vector representations. One such very naive representation is called one-hot vector representation. So in one-hot vector representation, you would have a vector of length of the vocabulary, and in so basically in document which word is present and which is not, that can be represented by this one-hot vector representation, where just single one has been marked on that word which is present in document. And also term document matrix, as you can see, where a collection of documents which have been mentioned in columns, and the frequency of the words that are present in documents have also been mentioned. More improved representation would be a word matrix, where a certain context, target, word association is also measured. So from this word matrix, we can figure out something which is called point-wise mutual information. So you can see the definition of point-wise mutual information, and another variant which is called a positive point-wise mutual information. So the definition goes something like this. So the positive point-wise mutual information would be max of 0 and point-wise mutual information, and point-wise mutual information is log base 2 of Pij Pi star into P star j, and Pij, Pi star, P star j, they have been mentioned here. Okay, so they are all dependent on the frequency of the term that you are trying to have a look at, or the words rather. So in the blue in this table, you can see the context, and the words are in red. So you initially have a matrix like this, where the words are marked in red and the contexts have been marked in blue. So the count of count of occurrence of the words in those contexts. These have been mentioned. These have been counted. Now, from this matrix, we would try to derive the probabilities as well. So the probabilities have been calculated, as you can see here. So probability of the context, probability of the words with context. So the point-wise mutual information has been calculated here, as you can see, given a few words and a few contexts. Okay, so now we the sparse vector representations are not able to meaningfully embed the context in which a word exists. So for that, what we do is we try to use something known as distribution representation of the words. So by using the distributional hypothesis, what we say is that words occur in contexts of words which are very similar. So like an example which has been shown here, the context of word banking has been represented in these three sentences. You can see the word which is banking, and the context you can get from the words which are around this word banking. Okay, so now let us try to figure out a game. So given 4 contextual sentences and some blanks in them, can we try to figure out what to put inside those blanks? Which word should we try to put in those blanks? Okay, so if we can understand which word to put in those blanks, we have to understand the context around it, right? So we can try to see that in some of these words we can put in C1, in some of the words we can put in C2, some words can be put in C3 and C4. So if you have words which can be put in most of these blanks, they might be very similar, right? So the first example and the last example, they are quite similar. So words that occur in similar contexts tend to have similar meanings. So this is the game that we are going to play, and eventually word-to-vec embedding, word embeddings, one very sophisticated and known word embedding, which is known as word-to-vec, has the basic concept, the basic intuition from which it has come is like this, something like this. So why should we use dense vector representations? Dense vector representations are much shorter than, for example, one-hot vector representations, and they need very less adjustments, and obviously the similarity inside the vectors are also captured. So now we are going to look into how what is the word-to-vec architecture, how the training is done in word-to-vec, and skipgram and continuous bag of words are 2 different terms that we are going to use in this, and these are some essential parts or essential terms that we are going to use. So in word-to-vec, as you can see, one example has been given here. 50 length vector for a certain word has been given. So given lots of document and lots of text, what we are going to get is large embeddings for each of the words. And the vector representations for each of the words should be such that they would effectively capture the meaning and words association within them. So one analogy that you can see, so here you can see word representations for king, woman, and man. And one analogy would be something like this: that if you try to perform mathematical operations on such dense vectors, what you would get is you would get something which would be similar to another word, which should ideally be similar to that mathematical meaning. So if you have king minus man plus woman, basically you are trying to shift the gender, right? You're trying to shift the gender. You are trying to say that what is the female version of a king, right? So, and you can see that after mathematical operations, you see that king minus man plus woman, this vector is quite similar to the word2vec that you word2vec embedding that you get for queen. So this is the overall skipgram architecture that is needed for word2vec. I will eventually come to this. Let us start from here. So the continuous bag of word is what we are initially interested in, and then we will go to skipgrams. So in continuous bag of words, what we do is we try to find out a word. As we had mentioned, we have a sentence and we have a blank, and we try to figure out that word. All right. So this is it. You have, say, 2 input words, and you are trying to figure out another word, which essentially will be the output word. So this is the model. This is a trained model. What should be the way to train it? We will come to that. So given this trained language model, ideally, if you put the inputs, it's going to give you the right output. It's going to come up with the correct output. So basically, it will come out with a certain percentage or probability for that word. All right. So the sequence of tasks that it is going to perform is it will look up. It's going to use a lookup table. It will look into the embeddings. It's going to take the embeddings. It's going to fetch the embeddings. It's going to calculate the prediction. And once it has calculated the prediction, it's going to project it to the output vocabulary. So this is something like that, what we had just mentioned. You are looking into the word embeddings. You are going to take the word embeddings, you are going to accumulate the word embeddings, and eventually you are going to come up with this 0.4, right? So now, how to create the training data set in order to figure out word2vec? So we can get lots of Wikipedia articles, and from Wikipedia articles, once we have taken the articles, what we do is we can take a small sliding window. So this red rectangular box is called a sliding window. So the middle word of the sliding window is the word that we are trying to target, that we are trying to figure out. All right, and we are saying that within this sliding window, we are trying to figure out not by looking at thou shalt make an A. If you have a look at this architecture, which is continuous bag of word, it says that we are trying to figure out W at T by looking at WT minus 1, WT minus 2, and WT plus 1 and WT plus 2. So now let us move back there. So we move the sliding windows and we figure out the input word and target word. So essentially this part is the second part, which is the skipgram part, where you are trying to look at the input and trying to predict the words that are around it. So what you do is you are getting the not, and you're saying that within the sliding window with not we have thou shalt make and a. So if you keep moving the sliding window, you can figure out something like this. For not, you will have thou shalt make a. For make, you are going to have thou not a machine, and like this. Okay. So you are going to figure out the training data set from here. Okay. So it's going to look like this. Okay. It's going to look like this. So now we are going to look at the untrained model, and we are going to try to train the model with all these. Okay. How to train the skipgram. Now we come to how to train the skipgram. So initially when we start with not, we are going to try to look and try to find out what is the word we are eventually getting from the output. And we see that we have, instead of thou, we have taco as the output, which is not right, because my actual target was this and the model predicted something else. So what we have to do is we have to calculate the error, and we have to update model parameters accordingly. Okay? So by using backpropagation, you have to update the model, and the untrained model will eventually, by feeding the instances, it will become a trained model. Okay, so you are going to train the model like this. Okay, so now for language modeling, one important very aspect is negative sampling. Why? Firstly, let us try to represent the problem definition in a different way. So let us try to change the game. Let us not try to just fill in with the words. Let us try to say that, okay, we are going to create word embeddings, very good word embeddings, and from word embeddings we are going to figure out the next word. All right, so from this task, the change task is something else. So instead of trying to predict the next word, what we are doing is we are saying that this is my input word, this is my output word, will they be in the same window? So the answer is now 0 or 1, so which is essentially binary classification task. So we have changed it to a binary classification task. So now with the binary classification task, instead of input target word pairs, we have input target words, or rather input output words, and a target class attached to it. So what is going to be the problem? Yes.
Sorry for interrupting. So you already have consumed 15 minutes. So I think it would be good if you can wrap up like within 2 minutes.
Yeah. Okay. So sorry. So this eventually turns out to be a single class classification. So for single class classification, what we do is we randomly take some negative samples, and with the negative samples we generate another data set. And for training word2vec, we need to have 2 more matrices, which are known as embedding matrices and context matrices. The embedding matrices are of size, vocabulary size into the embedding size, and the context matrix is also the same. You can once again see the embedding matrix and the context matrix over here in the actual architecture, this embedding matrix and context matrix. And now let us go back over there. So with the help of this, we can have the lookups. Now it's going to be extremely fast, and you are going to have this not and Aaron, Taco, and Do, we are taking 3 at a time. So one example is like this, and you can figure out the input dot output. The target is 1, so the sigmoid of the input dot output is 0.55, etc. So target minus the sigmoid is the error. So in order to update the parameters, what we do is we use the error in order to train this model and update the parameters, right? So essentially your Word2Vec would look something like this, where you can use mathematical operations on them, and you can figure out that the gender bias or plural significance of gender, significance of plurality, all these things you can figure out from here. Shortcomings of Word2Vec would be global information is not preserved, which is solved by GloVe, doesn't work well for morphologically rich languages, which is sort of solved by FastText, and lacks broad context awareness, is solved by even more improved models, which are LSTM, BART, and GPT. GloVe uses another objective function in order to optimize that. So the underlying architecture is still Word2Vec, but the extra thing that we try to use is a word-to-word co-occurrence matrix in order to capture the global context. That's it from my side.
Thanks a lot, Partho. I guess we can take questions from the room. Any questions? Okay, so if not, then we could try to set things up on this machine here. So let's take a small break of 5 minutes while we set things up from this side. And thanks a lot, Partho.
Thank you.
Okay, so after the brief history of NLP and what to bet, we are now ready to move on to the more interesting parts of the NLP pipeline that we see nowadays, which all uses transformer architecture. And that's going to be covered by Mr. Up to you.
Good morning, everybody. So myself, Mohammed, today I'm going to discuss about the deep overview of transformer based written language model. And so as Dr. Basjogri discussed that what today kind of models are actually useful to generate the vector representation for words, but the main problem with such type of models, this type of model contains the positional information towards generating or understanding the semantics of the particular sentence. So later on, NLP literature actually investigated some convolutional neural network based framework motivated from computer vision and literature, where they actually try to apply CNN on input text, so that to understand the semantics of the sentence given a text sentence. But the same problem occurs. This type of network cannot capture the sequential or temporal information. So for that reason, and to handle those challenges, the NLP literature witness and investigated the sequence-based model, where recurrent neural network is generally used so to capture the sequential structure. But as we know that the main problem with such type of recurrent neural network model, and that such type of model cannot deal with they cannot deal with long range or dependency due to the vanishing gradient descent problem when the input sequence will be very high. So one another problem in sequential nature is RNN-based framework is that such type of framework can take one input at a time. So for that reason, the training time is very slow. So to overcome these challenges, in 2017, in the Vaswani et al. From Google Research actually proposed the transformer architecture. So the right hand side figure is actually the transformer block, that it is based on encoder decoder this architecture, where the main component of the encoder module is the positional encoding, which actually helps to capture the positional information to process the input sentence and to parallelize the to make the training process faster. Self-attention mechanism they proposed, and in decoder part, same thing happens, except they introduce mark self-attention mechanism and make the training process very faster. And transformer can capture more long-range dependency accurately than CNN or RNN-based framework or HT-based framework. So after the invention of transformer, there are many language models actually offered into the NLP literature during the post 2017 era, and such type of written model can be categorized in C category, where retraining, fine-tuning, and prediction generally happens. And retraining can be done in three ways, that are encoder only, encoder decoder based, or decoder only model. Here I will discuss about the retraining of encoder only model, where the famous Marx language model is used. From the figure we can see that to train such type of network, actually, Lawson proposed that fill in the blank strategy. So let's say they randomly marks few token and try to predict those tokens and calculate the losses on those marks tokens. And using this strategy, they pretend the encoder architecture, and then on top of this is Devkin et al. 2018 proposed the bidirectional encoder representation and from transformer. So that is known as BART. So BART is also a pretend encoder architecture which actually pretend using the techniques of Marx language modeling and acceptance prediction task. And so after pretending this type of NPTEL encoder-based framework, BART is actually used for many downstream tasks, that can be sentiment classification, brand classification, or it can be data recognition, etc. So to actually here is the example that we want to classify whether the mail is spam or not spam. So for that reason, we have passing to the pretend BART module, and we have extracted the seamless representation from the BART module and pass it to the linear layer followed by sigmoid activation function, so that we can classify whether it is a spam or not spam. So after doing that, the main problem is pretending encoder based framework with if the task is like sequence to sequence generation, where machine transition or sequence or text summarization kind of thing, then we cannot apply such type of pretending encoder. For that reason, actually, pretending encoder decoder based framework is introduced into the literature, where there will be one decoder block during the pretending time, and there will be one decoder block also. So during the pre-training time, it will take the sentence that thank you, that it will marks few tokens, and it will try to generate those tokens with the decoder block. So it will nothing but work as a language modeling technique. And but the problem with this such type of literary encoder, when this type of encoder decoder based model is applied on classification tasks instead of sequence to sequence generation tasks or sequence to sequence text summarization tasks, then during different time such type of network takes lots of time. So for that reason, and so people investigated the decoder based model, so that will be discovered by
Hello everyone. Now I'm going to discuss about pre-training decoders. So decoders is actually a language model where we are giving input the sequence of words and we are getting output as the hidden states of those words. And now here you can see that suppose W1, W2 is those words, and after decoding we are getting those HT. Those are hidden states, and here we are discussing about the sentiment analysis problem where we have to classify if it is positive or negative. So in this problem, based on this architecture, we have given some words, and depending on that, we have classified if it is true or positive or negative. Now here I am going to discuss about LLM evolution tree. So initially I knew about transformer, where which introduced on 2017. So it was introduced by OpenAI. So after this, OpenAI, Google, Meta, all these platforms have introduced a lot of language models. Among them, Google introduced the series of BART, and OpenAI introduced a GPT series like GPT-1, GPT-2, GPT-Neo, GPT-J, all these things. And Meta introduced the Llama, OPG, etc. So what you can see in the right side, that depending on the number of parameters, as it is increasing, we are getting more, the accuracy is getting high, and we are getting better performance in our downstream tasks. So let us introduce GPT model, which was introduced on 2018. Here we have 170 million of parameters, and it is actually based on vanilla transformer decoder model, and it is trained on corpus depending on the books, where we have 4.6 dB text. This is all written actually. And next, on 2019, they have introduced GPT-2, where the number of parameters increased with the after increasing the number of layers, and also they have trained those models with lots of data, it's 40 GB data, and they also have introduced a data set which is known as web text, and which they have crawled from Reddit. And in this model, this is actually known, they have introduced zero-shot learning. I'll discuss it later. And later on, they have they told about GPT-3, where they have 175 billion of parameters, and in this paper, they have introduced about the few-shot learning. So, okay. So in that GPT-3 paper, together with few-shot learning, they have told about a concept which is known as prompt. So what is basically prompt? Prompt is basically, suppose we have a test instance and you want to know what is the output or what is the sentiment. Here we are talking about a sentiment analysis problem, and given a GPT-3 model, and suppose we have some given examples. Here we are seeing few-shot examples, and here we have to feed those examples into a prompt so that we get the sentiments. Here we can see that this is an absolute mess for the given above sentences, which is giving the sentiment as negative. This is actually known as few-shot learning. Now, in the middle section, you can see that actually the prompting may should enable the model to do any kind of task. It may be possible that the model is actually not trained for the task, like not trained in the task. So suppose here, first of all, have a fill in the blanks problem that JDK is developed by something, or there is some summarization problem, or there might be bar scan something. So bar scan fly. So the model should know the whole knowledge so that it can predict the future, or it can predict the what should be the next word. So here we have some examples where we can make the models to learn what the humans can think or what they believe according to the actions. So here, Pat is a person who is a physicist who knows that about the demonstration that the golden ball and the leaf being dropped at the same time in the vacuum chamber. So if he is a physicist, so he will know that they will fall at the same time, which ChatGPT actually given. Now suppose we are saying that Pat has never seen the demonstration before, and now we have the ChatGPT want to predict. So we will say, as it is written, that the ball will fall faster. So which is actually not right. So depending on the input, the output actually changes. Now we can see that actually if we give the prompt, we say the prompt that write the code on Python to arrange a sequence of numbers in ascending order, then it will give the code. I don't think we can do the mathematical reasoning things. It is actually easy, that's why it can solve. But for harder problems, we have to use chain of thought things, which later on we will discuss. So we have to use those things for the mathematical reasoning. So here we can see that the few-shot is actually don't need any fine-tuning process, and no gradient updates are also needed. Suppose in the first figure, you can see that the words are actually not arranged properly. So GAOT is giving the code, and similarly, you can see all the words, and which at last, if we give an unarranged word, it will give the original word. And then similarly in the last figure, so you can see as in zero-shot, the value is lesser, and as we are hiding the number of examples, then the performance will get better and better. Here is also an example. So more about this incontinence learning thing will be discussed by Dr. Ganguly. I'll hand over.
Okay, so before that, we have covered a lot. So maybe are there questions from the room on transformers or on GPT Okay, the emergent phenomenon, okay. So, okay, so let's try to summarize, because we have covered a lot. So let's try to summarize what we have known till now. Okay, so we started with NLP pipelines where we have the word vectors, we got one hot vectors, right? So you treated the words independently, and then you create a model on a specific task. Now that didn't give good results, obviously because words are not independent, right? So that's the first thing that the community wanted to address. So they wanted to have the real characteristic that words are not independent of each other, and you want to address that somehow. That's how word vectors came into being, where you represent words by dense vectors, right? And if you take the cosine similarities between the vectors, they are non-zero. They are non-zero, and that's what we expect like between words like atomic and nuclear, because they are similar words. So you don't want them to be dependent. You want the cosine similarities between those words to be high. And that's why you looked at the pre-training phase of noise contrast estimation, where you have large volumes of text, and then you take local window. Based on that, based on the work of co-occurrences, you can then estimate that words like atomic and nuclear, they're dependent on each other. So this is the first notion of generic task independent training that we had in 1-2. Beyond which we moved on to, and then if you feed on those bottlenecks in the NLP pipeline, it used to improve the results. So that was kind of an eye-opener, which pushed the community towards the self-recognition based approaches and like retraining on large language models, which again, like you take unsupervised text in lots of amount, and then you want to capture the semantic effects. This time not by the local co-occurrences, but by either by causal language models or by mass language models. And then in the transform architecture, we inbuilt the self-recognition mechanism, which means that it has lots of parameters that just for different conditions that you want to model. So this is massive volumes of pre-training that worked. And the effect of that pre-training is that these models with a very large number of parameters kind of get some emergent phenomenon. So like if you are looking at this example that Weil was talking about, so if you throw something like this to it, it already knows the semantics, right? So you can generate equivalent text. And the most interesting fact is that if you change the input slightly, like say for example, you are adding the fact that Pat has never seen this demonstration before, right? So everything else remains the same. And you are adding this as an additional context. Now it completely changes what a GPT-based encoder can offer, right? So this is interesting because if we are changing the input in predictable ways or in certain ways, then we can change the output. So there is functional dependence between the inputs and outputs that people are now trying to utilize for solving downstream tasks. So take, for example, a downstream task like text classification or sentiment classification. This can all be addressed. I hope this works, yes. This can all be addressed by changing the input that we are providing to the large language model, right? Now, that's the interesting time that we are living in, because we need to learn systematic ways and answer such questions that how are we going to change the input so that we can control the output. So there's one difference that I would like to point to you. So in supervised learning, we train the parameters based on examples. So we have the foundation models, say for example, BART or GPT, we have foundation models, and then we can fine-tune the parameters of those models on a specific downstream task. But that still involves training, and that still involves labeled data with considerable number of examples. Because if you are to fine-tune parameters, you can't just work with different examples. You have to have a considerable number of training samples to be able to fine-tune the parameters. But in context learning, we are not really learning anything. So what we are trying to do is, we are trying to control the output of the classifier based only on the inputs that we are providing. And in this case, we are relying on the foundation model's effectiveness itself, that if we are slightly changing the input, maybe we are providing a very small number of examples, then we are hoping that the foundation model will be able to generate something that corresponds to what we want. Now, the question here is that, how do we interpret the output of these models, right? So say for example, if you think, okay. So, so in this case, we are saying that, okay, so possible losses we're mentioning that is positive, negative, and neutral, right? So we are asking that question to the large language model, and maybe it comes up with the class negative. So in this case, it's easy to map between the word and the class because we are providing those words. But it may happen, it may happen that the class that it generates is not one of these words, right? So it's neither negative, nor positive, non-neutral. So then what can we do? So then we need to look into the probabilities of the words that it all generates, and maybe generate something else, maybe generate something that's related to the topic of the input. But we can still look into the probabilities of those words. So even if the decoder didn't end up generating that particular word that we're looking for, but we can go back and check the distribution of the vocabulary, and we can check, is the probability of negative higher than that of positive? So that's what we're interested in. So the first step in context learning is to define a set of words that will map to your classes. And ideally speaking, you just don't rely on one single word, but rely on a subset of words defining a particular class. Something like positive, good, great, that can be into the positive class. Negative, you can have disappointing, bad, something like that in negative class. And neutral, it could have words, right? So once you define that, this technically is called verbalizer. So once you define the verbalizer, you don't need to check if the decoder actually generates one of those words in verbalizers. You could just go and check the probability distribution. And all that matters is which probability is the highest. So you look into these classes of words and then take the one that's highest. Okay? That's how we map back the words from the decoder into the class posteriors for our downstream tasks. Okay. So is this clear? Because the hands-on thing is based on this concept, so make sure that this concept is clear to you. If not, then ask questions. Okay, so this is the simplest form of in-context learning where we provide examples. Yeah, so this is the example that I was talking about. So we are foundation model, you are not training anything, you are not fine-tuning the parameters. So these parameters of the large language model are frozen. All you are doing is providing some examples. So a new query is like a test instance for which you want to predict something, and usually it's more effective if you can find out examples that relate to your input instance. And if you're going to cite examples that have got no relation with what you want to classify with, for instance, then probably that's not going to affect your decoder's generation path, right? So it makes more sense to retrieve examples that are similar to your current instance. So this somehow relates to the concept of k-nearest neighbors. So k-nearest neighbors, if you want to predict a test instance, you have a training set, but you didn't learn any parameters from that training set, right? So all you have done is store the training set somewhere. Then given a test instance, all you have to do is to find out the nearest neighbors of that point. And you can apply the indexing based, and if it's like discrete text, then you can use an indexing tool. Or if it's like dense vectors, you can even have like approximate nearest neighbor tools for including similar dense vectors. But the whole idea is that you find the nearest neighbor of that point and then take a majority vote in KNN. The concept is kind of similar because you need to get these nearest neighbors given in this instance, right? So there is motion of retrieval that you need to do. And in this case, there is examples have labels, but we are not going to take the majority of the labels. What we're going to do is like append these examples to the input string and going to feed that as input to the large language model, hoping that with all the context, it should be able to figure out the correct word for this particular input instance. And from the word probability, we can then map it back to the class possibility. In this case, if there are two classes, all we want is like, is the probability of positive higher than negative, and that's what matters, right? Okay, and then this process can be more complicated, so we could have like multiple stages in our pipeline. So I'll just give you a very simple example. So this example is a bit complicated, but I'll try to give you a simpler example. Let's say you want to predict the sentiment of not one single sentence, but of a bigger document, right? So in that case, you could directly ask it, like, okay, so this is my big document. So you could form that as a part of your prompt, and then you could have examples, and then you could have a standard in-context learning flow. But that probably is not going to work because of the big context, right? Because the document is multi-article, and then you want to filter out information. So the first thing that you would ask in a large language model is that, given this big document, summarize this document or show me the keywords. So that would be the first instruction that you feed into the large language model. Depending on the answer, you could again feed that part for your another question, right? You could say, okay, so given that summary, tell me the sentiment of this document. So it's this multi-stage pipelines that we can do with chain of thought prompting. So we don't have to necessarily have like one single prompt. We can use a feedback loop with the large language model, where we prompt it the first time, we get a response, we again prompt it with that response back to it, and then we can do it multiple times to get my desired outcome. Remember that every step you have to be aware of how to interpret outputs and how to use them. That's a very generic notion of channel. So I don't think I will have time to cover anything else, but I have some more slides, some examples. Probably I'll just show this example. So this is one of the challenges that we need to face in context learning nowadays, because there is no clear way of how to set your process, right? So just this example, it shows that, this is a difficult example because it says that it's a convoluted way of saying things, that movie was really great, if you're jumped beyond imagination. There is some kind of sarcasm, right? So, and then people asking the large language model, that sentiment expressed in that sentence is, it is easily moved into saying that it's in the positive side of the range, whereas it's not. It's a negative sentiment, right? So what can we do? Maybe if you look at the other prompt. So we change that prompt, where we just say, consider the following sentence, that movie was really great, if you're jumped beyond imagination. So, no, stay there. So this is this part that we added. If you just added that part, the sentiment changed very quickly. So you can see that how not robust is a large language model, or how vulnerable that is to what you are filling in. So just by this prefix, such as the following sentence, it has changed its prediction from positive to neutral. And if you look at the next example, that movie was really great, if you're jumping beyond imagination in the author's opinion, the movie is. So that's a very small change that we made, right? So we are introducing another subject to this sentence, but that has a big effect in changing it to negative, which in this case is the correct sentiment that we wanted to bring. So really there is no obvious way of how exactly you tune the prompts to be able to get the correct predictions. And that's a very interesting time that we're living in, because there are many research questions that are not yet explored. And I think it's a very good time when researchers explore all these questions and to be able to effectively improve in-context learning. There are advantages of in-context learning, and you should realize that, because it requires a very small amount of training data, because we are not training in parameters, as per se. So we are just trying to utilize foundation models most effectively. So there is no training involved, so it's extremely fast compared to like supervised pipelines where you require lots of training data. So that's a very good advantage of in-context learning. But on the flip side, we need to have more like established ways. Like supervised learning, we know how to deal with those, because there are very listening approaches on all established techniques. that works. But in this case, we need to find out more controllable ways of control interpretations that we want from the large language models. These are many interesting set questions in this, and I won't have time to go through all of that, but let's move on to the hands-on tutorial, where we'll be finding some 4 examples where you can like play around with in-context learning, right? Meanwhile, if you have any questions, we'll speak with yours before we move on to the hands-on practical session. Yes.
English is spoken in many parts of the world. There are Indian English, UK English, US English. How do that actually talk about it?
Large language models are trained on everything. So it has ideas about Indian English as per se, dialect, and the normal English functions. So, but I think Indian English won't be forming a large part of the experience set. So in that case, our new context learning is all about using examples, right? If you want to summarize a document that's written in Indian English, you can put an example that this is how an Indian English document looks like. So I have tried to test the GPT, we have a GPT, and if you get it to like generate Victorian English type of documents, it can generate some things. So although it doesn't form the majority of its training set, but all these many parameters, it can handle different small amounts of data. So it should be able to learn effective representations also from like a small proportion of data. Good. Any other questions? Okay, so I think we can just move on to the hands-on stuff, which is more important than all this theories. And we're running short of time anyway. Okay, that's good. We have the collab too.
So now I will discuss about how to apply in context learning on sentiment classification task. Okay, so I will go through the code in Google Colab notebook. So I am actually using the GPU runtime. Okay, default GPU. So if you have so GPU memory is like 16 GB to load the large language model which we are going to use for the sentiment classification tasks. So we are using 75 large here as an instruction tuned large language model. So initially I what are the modules that I am going to use to conduct that experiment. First I will discuss about those libraries. So first one is sentence transformer. So sentence transformer is actually used for to get the dense vector representation for each and every sentences that is going to be classified as positive or negative, both for test and training instances. Similarly, I'm going to use PI's GPU to actually generate the neighborhood samples, get the neighborhood sample, and we are using Hugging dataset module to get the sentiment classification datasets, and accelerate it used to load the large language model into the GPU memory. Okay, these are the required libraries that you need to be installed. So that then these are the additional libraries that are required after the installation is done. So if you import this, if you run this notebook, so all the things will be loaded, which are required for calculating the accuracy. We are using scikit-learn module for loading the dataset. We are using the Hugging Face dataset libraries, and to visualize the dataset, we are using pandas. So, now I will discuss about the dataset. So this is the description of the dataset. So here we have painted 10 samples. So this is the input, and raw is something is there, and this is the output level of the dataset. So here 0 means it is negative sentiment, and 1 means it is positive sentiment. Okay, so now I will split the dataset into 2 parts, like training and testing. Then to conduct the in context learning framework, as I was telling that it is important to give labeled example. So for that reason, we have need to for each and every test instances that needs to be classified, we need to actually get the required labeled training sample. So for that reason, we are using the PI's module here. So it will try to calculate the neighborhood or nearest neighbor for each and every test instances, and it will try to get the required training instances, and based on that we will generate the prompt accordingly. So to load the LLM model, we are using this part auto model for sequence to sequence LLM, as FANTI-5 large is actually sequence to sequence leveling language model, which trained on sequence to sequence leveling tasks. So for that reason, we are using auto model for sequence to sequence LLM, and so to get the DNC presentation for training and test instances, we are using sentence transformer, and the required BART we are using. Here anybody can use any written language model, whatever they want to use, and based on that we create the PI's index, and to generate the few short samples. So we are using this function. So pfQsort, when we are using, suppose we are trying to actually get the top 5 samples, we will pass top k is equal to 5, and for each test instances, we will try to search the nearest neighbor of top 5 examples using PI's index, and that code will be like this. This will return the required prompts, as well as the required neighbors, required neighbors for the particular test instances. So if we see the output for this, like, so for k is equal to 1, so the prompt is like your task is to predict the tone of the sentence into 2 classes. So after that, we are giving one level example. Here are some example are given below. So input is like 2 depth by half, but supremely good nature the level. So this is the training instance, and the label is already given positive. Now it will try to predict what will be the level for that particular test instance, like PT can go despite its summary things. So, to now, this is you done using say cosine similarity or similarity based metrics, where if we apply if we randomly retrieve some samples for each and every test instances, then we can get a labeled example for a particular test instance, and if we compare the performance versus similarity based retrieval model and randomly retrieved examples, then we can see that the accuracy for that particular model will differ. So for the random, the accuracy is like 53.5, and for Pi index, it is like 53 in for k is equal to when k is equal to 1. If we increase the number of labeled example like 2, 3, 4. So here we have got the highest accuracy for k is equal to 5 by 3. K is equal to 6. So here the accuracy is like 53.5 for 5, and for random also. So we are actually conducting the experiment on a small set of examples, like 20 samples we have taken. So if we take whole purpose, then the accuracy may change. So this is one type of techniques, and another example we discussed. You have inquiries on this notebook, please ask, and we will share this code. Then you can go through the code.
The code is something that we'll share with you all, but make sure that you understand the basic concepts that are being shown here. I guess that's kind of clear to the audience. Not then ask questions. So this is without using any libraries, not the question. From here, the audience has to hear what you're saying. From here.
So the question is like how to assign, how to load the dataset in different datasets you was asking. So we are actually taking the sentiment dataset, inbuilt dataset that is already available in this library. So if you want to actually conduct the experiment custom dataset, then you have to feed your dataset in this format that we have shown. Like you have to just put the sentence in text column. You have to just make one CSV file, and text will be on one column. It can be anything, and there will be one thing that will be the label column. Okay, so you have to put the sentiments here, and the text is here. Then you can load the dataset using pandas read CSV. Okay, and then you can apply this code. Is it clear?
This has got nothing to do with in-context learning. I mean, any Hugging-Face pipeline has to follow the same loading of the data, right? So this demonstration is without using the specific libraries for in-context learning, like LangChain or TensorFlow. So this is, if you just want to use Hugging-Face and build on an in-context pipeline from scratch, from the first principles, that's how you should do it. Okay. And then in the later part of the tutorial, we will be covering OpenPrompt and LangChain.
That will be covered by Sriman.
So, now the Muzgun course has said about application of in-context learning right from scratch. Now I will show how we will use some renowned libraries like OpenPrompt or LangChain to conduct the sentiment classifications. I am audible. So this is the tutorial on OpenPrompt and LangChain on sentiment classification tasks. So first we have to, as Muzgun said, that first we have to install all the libraries that will be used in this tutorial. Additionally, from the previous notebook, here we installed OpenPrompt and the LangChain. So after installing these libraries, we will move on to the import. So additionally, we have to import this OpenPrompt from prompt classifications modules from OpenPrompt and the input example in these three parts. So after that, we will move to the next part, that is loading of the dataset. This is the same from the previous notebook that we used here, the same datasets that demonstrated the previous. So after it's the same example that we choose. So same function. And now, as said, we mentioned that future learning can be we can use a verbalizer that will map. Since we know that if a generative model can generate some bad text, like I want to generate the sentence is classified as positive, but the generative model can generate that the sentence is classified as a true. So we have to map that to the positive. So we need verbalizer. So this is the main crux of OpenPrompt, that we can implement verbalizer manually. So for example, positive can be mapped to true, positive can be mapped to good, positive can be mapped to wonderful, and similarly the negative sentence, negative term can be mapped into bad, worse, etc. So on that basis, we however the model will generate this type of things, it will be mapped to the positive or negative class. So future learning based in context learning using OpenPrompt. So for this reason, we need a verbalizer. So this is the way we will import the Google Flyme large model in the notebook. So using OpenPrompt. After that, this is the thing that I said, that global positive or global negative list, where each global positive means positive can be mapped into true, happy, good, excellent, these words, and similarly negative can be mapped into bad, poor, terrible, etc. So this is the main part of the verbalizer. So as from the previous notebook, we can see that we can use sentence transformer to generate the sentence embeddings. So here we also use that things. So next we will use these are the similar kind of libraries that we have previously shown in the previous notebooks. So after getting that, we will came the main part of the code, that is this is the main part where we utilize the verbalizer plus OpenPrompt library to generate the class of the sentence. So basically this is the template function where to conduct the sentiment classification for from scratch, we will need to implement those things manually. But in the open prompt, if we insert the manual prompt function and we will and if we manually if we format the text as the open prompt manual template prefers, then it will automatically create the prompt list. So we did not have to explicitly keep the prompts. So this will help us very much quickly to import the results. So this is the way we will given all the things from using the program library, and finally we will obtain the results that we obtain that this if we run this cell, then it will print these things. After that we will get this is the after implementing the formalizer, the result gets inputs. So this is the main things that OpenPrompt can help us. So after that, I will give a small introduction of LangChain. So LangChain is a widely used library that helps for programmer to incorporate OpenAI's APIs and other things into their project. So in the LangChain, there is an important function called sequence, called chains. For example, the input one has some prompt and with corresponding some text. If we pass to the LLM will give some output. And if the output, after getting this output, we pass to the LLM again, and we get the final output. So here, if we utilize these things in sentiment classification tasks, we will see that if we see that this is the thing that this is the pipeline that we use to generate the chain 1 and chain 2 utilizing the LangChain library. So here we see that after running this cell, we will obtain that this is the main sentence that offers the rare combination of entertainment and education. First, we prompt that extract the important keywords from the text. So the LLM extract that offer education combination of the important keywords, and after getting the important keywords, we will classify whether this on the basis of these keywords, whether these sentences are mapped into positive class or negative class. And the LLM says that it's mapped into positive class. So this is a small example. We can build a very large library, very large software on using this LangChain methods. So this is the from my side. So
if you have a question, audience, please. Any questions? Yeah, I think it's important to get the concept and then obviously can look back at the code. This is all we shared with you. And I guess that we can map back the code to the concepts that. So if there are no questions, then I think that's pretty much it from our side. And thanks to the speakers, all the speakers, Shrudeep, Partho, I don't know if they're online or not. But thanks to everybody and thanks to the audience for attending our tutorial. Thanks a lot. That's it. Thank you.